So it's a real pleasure to introduce Erkki Somersalo. I'll just do a very short introduction for those of you who, well, I think nobody needs an introduction from Erkki, but anyway, Erkki is a Finnish mathematician who speaks Italian, by the way. He's also a famous cook and now lives in Cleveland, US. I would say he's a world-renowned inversor, provided that inversor exists as a word, with many articles on MEG in particular. I should recall he's one of the 3 authors on the article on minimum current estimate, 1999, I think, in which they basically used the first sparse, well, provided first sparse solution for MEG source localization. And he's a Bayesian, of course, which I like very much, very, very much. So it's a real pleasure to have. I asked Erkki to provide a kind of a very long overview on the inverse problem, of course, and it's a real pleasure to now let him speak. Thank you, Erkki.
Okay, thank you, Albert, and thanks to everybody who has been organizing this conference. It's a great pleasure, and I, of course, would prefer seeing you all in person, but life is what it is, and so welcome to my messy office. So instead, so yes, I'm going to talk about sparsity, sensitivity, and model selection in MEG, and in particular, the sparsity and sensitivity will be in the focus of my talk. And so let me start with, in a rather unconventional way. I'm starting with the literature, which people usually show at the end. And this is simply because I want to, outline a little bit the story, why this talk is what it is, and so where it comes from, and so on. And in particular, I want to emphasize who has been working with me on these topics that I'm going to present. So here are a couple of articles that we wrote more than 10 years ago with Daniela and a number of then students. So there is, you can see Samsa Pursiainen, many of you know from Finland. So we were starting to look at these hypermodels, Gaussian hypermodels for MEG at that time. And so we realized that this is a really versatile approach to inverse problems, and MEG was sort of the application that we wanted to apply it to, because first of all, it's so important, and we knew that the sparsity issues are sort of central there. So then we had a couple of papers with our student Laura Homa, with Daniela, and there's Alexander Hoover too in the second paper. So these papers were applying these hypermodels to a particular question, which is source separation. So you may have a source which is sparse, and then another source which is, you can think of it as a noise source, and so you'd like to separate those. Question is, can you do that? And it turned out that these hypermodels are actually providing you some tools to do that, and so we applied it to this question. Now, at the end of the talk, you may, if you have time, I will revisit a little bit this question. So in 2014, I believe, Daniel and I were in Rome, and we started to work with Francesca Pitolli and Barbara Vantaggi and Annalisa Pascarella, who is also here. Nice to meet you again. And so we were, so the idea was to use these hypermodels to analyze a particular set of data which was related to meditation. And you heard yesterday Daniela talk about that research, and that collaboration led to these 3 papers where we are sort of developing systematically this hypermodel idea for MEG. So not just hypermodels for inverse problems, but in particular for MEG. And so most of the talk will be using results which are going back to these articles. And then recently we have been working with other students. So Alexander Strang was our PhD student here at Case. And then Monica Praiola, who is in Bologna, joined the team. And so we were developing further these hypermodels, not necessarily for MEG, but in general as inversion methods. And so there's an ongoing work with Monica. So the last one is a preprint that you can take a look at if you wish. Okay, so what are we talking about? So I start with MEG problems. So I'm setting the scene, talking about something that you all know very well, but just to fix the notations, I think it's important that I go through the forward model too, so that my notations are not ambiguous. So we are starting with quasi-static Maxwell's equations, and we write the magnetic flux density B as a function of the total electric current in a domain omega, which is modeling the head. And so the well-known formula for B, integral formula coming from the integral formulation of Maxwell's equation, is given here as PR is the integral of essentially the total current cross R minus R prime scaled with the third power of that. So that's the starting point. Now the total current is the impressed current, which is the brain activity that we are primarily interested in, minus the volume current, which is equal to sigma times the electric field with a minus sign. Oh, well, no, sigma times the electric field, and the minus sign is because the electric field is minus gradient of U, where U is the electric potential. And so now if you assume that there are no sources or sinks of the total current, then taking divergence of this equation will lead us to the equation for the potential. This is a linear PDE, and so if you know J, you can solve this because you have the Neumann boundary conditions telling that there is no current flux out of the head. Okay, so the forward map is that if you are given J, the impressed current, and sigma, you should be able to compute B. And Carsten Wolters is an expert that can tell you more about, the intricacies of solving this numerically, and I think his talk is what you should look at when you address this question. So I'm not going into details. I'm just saying that since the problem is linear, so J depends linearly on U, and U depends linearly on J tot depends linearly on U, and U depends linearly on impressed current. So the B is linear in this impressed current, and so you should be able to find a kernel G sigma, which is mapping the impressed current to the magnetic field. So you can call this a lead field tensor if you like. So it is a vector valued a matrix valued mapping. And so then of course we do the discretization. So you can think this as a quadrature, a numerical quadrature. So the integral is approximated by a finite sum where you have weights Wj and you have the nodes Rj, and you are evaluating your impressed current in those nodes Rj. R capital K is the location of the magnetometer, and gamma K is the direction, the normal direction of the surface of the magnetometer. And so that's what we are measuring. And so then if I denote by Qj the source dipoles, which are the pointwise values of the impressed current, and I denote by Lj the matrix of size m by 3. When you take the dot product with gamma, these 3 by 3 matrices become 1 by 3 vectors, and so I'm stacking them into a matrix. And so then my data, noiseless data in this case, according to this model, is this vector B. I have m magnetometers, and so then you are having a matrix vector product, which is telling you how you calculate this B. And these Ljs are then the lead field matrices. And I can, of course, collect all of them into Let me see. Yes. Okay. So this is fine. I'm collecting them later. So here is a schematic picture. So you have the brain region, and suppose this red one is a single dipole. So what you need to do, you have to calculate first the electric voltage, assuming some conductivity distribution of the brain, which in this schematic picture was taken to be constant. And so then you see that the voltage on the surface of the brain, which is mapped here in the middle picture, is showing a dipolar pattern. And so then taking into account the voltage distribution and the impressed current, I can calculate the magnetic field. And so the last picture here is showing the normal component of the magnetic field. And so you see the typical butterfly pattern. So the red buttons mean that there's a current magnetic field out of the source, and then you have these blue dots, which tells you that the source is going in. And so the neutral spot in between is basically where the dipole is. And so looking at this picture, an expert can tell where the dipole would be. So makes sense. Okay, so here is my further notation. So Q is a vector where I stack all my current dipoles, and each one of those n dipoles has 3 components. So this is a vector of length 3n. And so then I can write this linear combination of the contribution from single dipoles as a matrix vector product, where my matrix L is the lead field matrix, where I have collected these m by 3 matrices in groups of 3 columns, and so L is the total matrix here. Oops, so let me see. So the inverse problem, of course, so this was the forward problem. Then the inverse problem is that suppose you are given the observation B, so then and there is noise epsilon, so then your problem is to try to reconstruct this vector Q based on your B. Now notice that I assumed here that the sigma is the conductivity is known, which is not. And so ideally you should of course try to estimate the sigma too, but we know that this is a rather challenging problem, so I'm not considering it here. However, this is sort of a plug-in model that I'm using, so I'm assuming that I know sigma, although I don't. So what does it mean? It means that I have plugged in a known, presumably known value for sigma in my L. And so therefore, there is some sort of modeling error here, because that sigma is likely not to be the correct sigma. And so you should address this modeling error. So in my notation, I implicitly assume that this epsilon, the noise, is not only the exogenous noise or the noise coming from the brain, but it's also containing the modeling error. So the modeling error is a different topic. I'm not going to address it, but just let me briefly tell what you can do with it. So you can think that the modeling error is the difference between LQ, where we use your plug-in model, minus LQ, where L would correspond to the true conductivity. Now your problem is that you don't know the conductivity, the true conductivity. But what you can do, you can sample from some prior distribution several candidates for this true conductivity and compute the differences. Now the differences then are sort of realizations of the modeling error, and so then you can do statistics to model the mean and variance of the modeling error, for instance. And often it helps a lot in many inverse problems. This sort of modeling error approach is truly helpful, and I believe that in MEG that would be also very helpful, although I don't think that it's systematically done. I believe EEG people, my colleagues in Kuopio, did it with EEG but not MEG, so maybe that's something that could be looked at. Anyway, so I'm assuming here that there is some error epsilon, which is including the modeling error, and my LQ is the model that I'm using for inversion. So as Alberto kindly pointed out in his introduction, I'm a Bayesian, yes, and I like the Bayesian approach, and not only because it's very effective mathematically, but also like the sort of the philosophy of the Bayesian approach. So the idea is that if you don't know a variable value, you model it as a random variable. And the randomness is an expression of lack of your knowledge of the true value. So it doesn't mean that the variables that we model as random variables are random in some ontological sense. So they may be very well defined values. We are just not knowing the values. And so that is what the randomness here is expressing. And all the randomness is then encoded in the probability densities. And so the probability densities are expressions of what uncertainty we, in our knowledge, we acknowledge. Okay, so what is particularly nice in this this Bayesian approach is that it explicitly makes you state what your prior is, so what your a priori bias is. And so we often think that, well, we can use some sort of flat priors which are non-committal, but you know, the priors are always telling something about our our bias. So just to give an example, so if you ask people to pick up a number, usually you get the number from I don't know, from 1 to 100. Although if you think that any number, the probability of any number being in that range is extremely low, if not zero. So, but if you ask anybody and you get the number which is basically from 1 to 100, which tells us that our prior is really towards small numbers. So this is a sort of an implicit prior that we have. And when you're a Bayesian, you should somehow try to quantify that sort of observation, and so that is what you put into the prior. So prior is important. It's also important to think about what your prior is, because that helps you to analyze what you're doing. And so this story that I'm going to tell you about these hierarchical priors is pretty much sort of following this idea that we need to be careful and think what the prior is really telling us. Okay, but before I go to priors, I'm talking about the likelihood model, and for simplicity, to make things easy, I'm assuming that my observation noise, remember, which may also contain the modeling error, is normally distributed. Well, if you take the modeling error, usually the modeling error has a non-zero mean. So this epsilon should probably have a non-zero mean, but for simplicity and notational convenience, I'm assuming that my epsilon is zero mean, because you can always subtract that mean from your data if you know what the mean is. Okay, and sigma is a symmetric positive definite matrix, which is a covariance matrix of your error. And so knowing that, you can write the likelihood density, which is the probability distribution of your data, assuming that you know your Q. So the only randomness in this case, let's go back here. So if you look at B equals LQ plus epsilon, if you know Q, the only randomness is from epsilon. And so therefore the distribution of epsilon determines the distribution of your B, but you shift it so that the mean is around LQ, which you're supposedly knowing. And so we have this typical Gaussian likelihood model here, and I'm denoting this this quadratic form B minus LQ transpose sigma inverse B minus LQ by using the shorthand notation that it is a sigma norm, where the sigma enters in the norm through its inverse. So that's the simple model for my likelihood, and I don't care about the normalizing constant here, because there's nothing unknown in my likelihood, and so therefore I can always normalize if I need my likelihood, so that the integral over B is equal to 1. Now the prior model, let's go to the prior model. So as I said, the prior density by Q is encoding all the prior information about the Q before you start measuring your B. And as you will see in this talk, sometimes when you build this prior, you may also want to think a little bit ahead what your measurement is going to be. that's, I think, legitimate because you know what you're going to do. So it is not that you are in complete empty space and then somebody gives you data. You know what the measurement is going to be, so you can think about in advance what kind of questions you should ask before you set up your prior. So you will see what that means. At this point, I'm just saying that the prior is encoding what you believe before you take in the data of Q. And quantifying your prior is the hard task in inverse problems, because often our information is qualitative in nature. So finding a quantitatively useful prior, which is sort of encoding what you qualitatively think, it's a challenge. So once you have that prior, then you can use the celebrated Bayes formula, saying that the posterior distribution, that is the distribution of Q given the data, is obtained by the joint distribution of Q and B divided by the marginal distribution of B, and then you write the joint probability distribution of Q and B as a product of the prior and the likelihood. And so often we don't care about this marginal density, which is the denominator here. So it is some number which is a fixed number because B is fixed. You fix your B to the observation. So it is simply contributing to the normalization. So if you need to force that the integral of your posterior distribution over Q is 1, then you need that normalizing constant. Usually we don't care about that. So the usual way of stating Bayes formula is that the posterior is proportional to the prior times the likelihood. And that's what I'm going to use here. Okay, so now let's start looking at the priors. So there are several simple priors that people have been using through decades in MEG and in other problems, and I'm showing you 3 of them which are sort of very characteristic, and then I'm going to talk about the hierarchical model. So one of the most straightforward priors is called a white noise prior, where you say that the individual dipoles are a priori mutually independent, first of all, and they are sort of identically distributed in the sense that the a priori assumption about the energy of each dipole is the same. And so if you if you write that prior in a quantitative manner, what you get is simply an exponential of -1/2 alpha squared and the sum of the squares of your dipole. So alpha squared is the variance of the amplitude of the dipole, and so that is determining what you think about the energy of each dipole. So tweaking with alpha, you can change the width of this distribution, how close to 0 you assume that the dipoles are. So that's what the role of alpha is. So this is not very interesting, although very useful and widely used prior. So let's look at something a little bit more sophisticated. So smoothness priors are typical priors that people are using. So what a smoothness prior says in words is that the individual dipoles are mutually correlated. So nearby dipoles are strongly correlated, far away dipoles are typically less correlated. So they are forming a vector valued Gaussian field. And the idea is that you can decouple this Gaussian field by applying a differential operator on the Q field. And differential operator in this case is, of course, a discrete differential operator, because I have discretized my current density. So the idea is that you design an operator D such that D times Q is standard normal distribution. So this is a decoupling or whitening. So you take your Q field and you apply this D, and then you get something which is white noise. And so using the distribution of the white noise, this gives you the prior model where you have in the exponential, you have 1/2 times dq squared. So this is the typical form of a smoothness prior. Now, what is this D in general? So people are using different differential operators. So here is an example. So suppose you have a cortex model where you have sort of the dipole positions are vertices, and then you make a Delaunay triangularization of the surface. Now you can tell which dipoles are neighbors in your graph. And so then you can design a graph Laplacian. So you take the dipole in a node, and then you subtract 1 over nj times the sum of its neighbors. So you take the mean value of the neighboring dipoles, and then you scale by some alpha. And this is the jth component of dq. And so having this, you can easily write this D matrix is going to be a sparse matrix, which depends on the neighborhood structure of your dipoles. So J twiddle K means in my notation that these nodes J and K are neighbors in the triangularization of the source space, and Nj is the number of neighbors of the jth dipole. So what is Prior is stating, in other words, is that you think that your Qj is always the average of its neighbors plus innovation. So that means that if you wouldn't have this innovation, your Q would be exactly the mean value of the neighboring dipoles, and then your dipole field will be a graph harmonic field. But so of course we don't want that because there's nothing to solve in that sort of case. You know exactly what to do. So you pick one point and then the whole thing ensues. So you need to have some randomness, and the randomness is exactly this WK, which is normally distributed. Now this graph Laplacian is kind of a global smoothness. So as you know, harmonic functions are very rigid. So if you change a harmonic function in one point, it changes everywhere in space. And so sometimes you want something which is less rigid. And so what people are doing is they are adding a term which is shortening the correlation length between the dipoles. So the family of Whittle-Mattern priors are very popular. So you modify the graph Laplacian by simply adding a term which is related to the correlation length lambda. And so playing around with this lambda parameter and alpha parameter, you can create sort of smoothness priors which are kind of lumpy, and the size of the lump is encoded in this parameter lambda. So we are sort of inching towards the case where our prior depends on parameters. So this lambda is a parameter which is in your prior. Now, if you are confident and comfortable with your prior, you can just write down the prior with all the parameters. However, you might even ask, is it possible to get information about these parameters in your prior based on the data? So this is one of the questions that I'm addressing in this talk. Before doing that, let's mention one more class, and this is also relevant for my talk today: sparsity prior. So often we know that what we are looking for is sparse or compressible. So in this case, what does it mean? It means that we are assuming that most of the dipoles that you have placed in your brain model should be 0 or close to 0. So, but you don't know which ones. So some of them you believe are non-zero or are above a given threshold, which is the way of saying that this is compressible, and the others should be below. And so since you don't know which one should you choose out of the many dipoles that are non-zero, otherwise you would know exactly where the activity is, you want to have a prior which is favoring solutions where most of the values are close to 0. And it is well known that L1 norm, and in this case it's L1R3 because I'm looking at the L1 norm of the norms of the dipoles. L1 norm is a norm which is favoring typically solutions that are possibly having some outliers, and those outliers are the dipoles which are non-zero, while the others are basically 0 or close to 0. And so this prior has had a significant success in inverse problems and in compressive sensing. You all know about the compressive sensing L1 magic stuff. So this is basically the prior that we're looking at. And so then, of course, once you have the posterior and the prior and the likelihood, and you have the posterior. So if you say that this posterior is your solution to the inverse problem, usually people are not so happy because you should show also some pictures. So based on the posterior distribution, you should produce some estimates. And so one of the most popular estimates is the maximum posterior or map estimate. So what is the map estimate? It is the maximizer of the posterior distribution given the observation. Of course, you have to assume that this maximizer exists. So you may have cases where you have several local maxima, and some of them are close to the global maximum. And so this may be a little bit ambiguous in multimodal cases. But often it is a convexity issue if you have this well-defined unique maximum or not. So I will address that soon. Okay. So, but for the time being, I'm not concerned about that. I'm assuming that this maximizer exists, and so then let's look what this maximum posterior estimate looks like in these different in the different examples that I addressed here. So if you take the white noise prior and you write the likelihood times the prior, you see that the maximizer is the minimizer of the minus log logarithm of the posterior distribution, and you end up having you have to minimize this term where you have the fidelity term and you have the penalty term, and of course you should recognize that this is the minimum norm estimate. One of the early success stories in MEG, going back to I believe to 80s even, and it's still widely used, and it's not a bad inverse solver at all if you need to do something. Minimum norm estimate is a sort of a quick way to produce nice, reasonable solutions. Joint sparsity prior, well, why joint? Because I'm assuming that the three components of each dipole are lumped together here. So sparsity prior is that you minimize the fidelity term plus mu times the L1 norm of the norms of Q. And so again, looking at this, you should recognize that this is the minimum current estimate, which produces nice and focal current estimates or dipole estimates. So that's also a map estimate. Now, I mentioned that your prior may depend on parameters, and so you would like to estimate those parameters if you are not sure about the parameters. So if you think that there is uncertainty in a parameter that you have put in your prior, you would like to estimate that too. And so here I have written the parameter-dependent Gaussian prior, assuming that the matrix D, which was the matrix basically in my smoothness prior, is parameter dependent. And so now you have two parameters. You have the Q that you are primarily interested in, and then you have this theta, which is parameterizing your prior. So what could this data be? So think about the following simple example. So you are not sure about how focal your source is. And you know that if you are using the white noise prior, you get independent dipoles. And on the other hand, if you use the graph Laplacian, you get a continuous current distribution. So what we could try to do is to take a convex combination of those two matrices. So this theta parameter is interpolating between the white noise prior and the smoothness prior. And if you think about the extreme cases, when theta is 0, you have the white noise prior. If theta is 1, you get the smoothness prior. So you see that this theta is encoding the correlation length between your dipoles. And so then you can ask, can I estimate this theta together with Q from the data? So can we learn the parameter from the data? So this idea we have been testing not with MEG but with other inverse problems, and if, let's say it this way, so if your data is sensitive to the correlation length, then it's possible to get information about this correlation length. If your data is not sensitive to it, so the smooth source explains your data as well as the non-smooth, then you're likely looking at a problem where the data is not enough to determine this theta parameter. So, but in some cases it works really well. So this is, however, not the problem that I'm looking at here. So as I said, in the Bayesian solution, if you have a variable or parameter in this case, which is poorly known, just model it as a random variable. So if you don't know something, you say that the ignorance or lack of information is expressed in terms of some random variables, and then you try to encode that lack of information in the probability distribution of that variable, which leads you naturally to the hierarchical prior model, where you have two variables, Q, your primary unknown, and theta, which is the auxiliary parameter. And so then you write the joint probability distribution, the joint prior, as the conditional prior, which is the prior that you just built, assuming that you would know theta. And then you admit, okay, so I don't know theta, so the theta has also its own probability distribution. Then the product of those two gives me the joint probability distribution of Q and theta. And so this density by theta is called the hyperprior. And now the joint posterior density is given by taking the joint prior density, which is the last two terms on the right of the last equation, times the likelihood. So now we have three terms. We have the likelihood, we have the conditional prior, and we have the hyperprior. And so those three terms together constitute the joint posterior density of Q and theta given B. And so now you can try to estimate both Q and theta from your data. And so this is the kind of problem that I'm interested in here. So we have two parameters, Q and theta. So if we want to show, let's say, an estimate like maximum posterior estimate or something else of Q, we should have a good strategy to solve for a likely representative Q. And here the path is bifurcating, so you can do many things, and all the roles that I'm going to briefly review here, they have been studied extensively, and they are all, meaningful ways of looking at problems, but they may have some technical issues. So first of all, here's one strategy. So suppose you are not really interested in this theta. So you know that there is uncertainty of theta in your model, but you're not really interested to know what this theta is. So the typical technique in Bayesian framework is that you integrate out the variables that you are not interested in. You marginalize them. So in this case, you take the joint posterior density of Q and theta given B, and then you integrate out this theta. And so then you get something which is only the posterior density of Q given B. And so then you can apply your maximum posterior estimate, for instance, to estimate Q. Now, this looks like a straightforward road to take, but there are certain issues here. One is that the marginalization is not simple. So if you have one single parameter, one scalar parameter, you may be able to do this marginalization or the integration even explicitly or analytically. If you have several of them, we all know how hard it is to calculate high dimensional integrals let's say, using quadratures. And so quickly, when k is increasing, you have to resort to Monte Carlo integration techniques. And then you are in a different world again, so because you have to have a sampling strategy and so on and so forth. So the marginalization is not usually simple, and the resulting marginal posterior may be rather difficult to deal with. So there may be some determinants, etc., that you have to deal with, and calculating them may not be easy. So there are reasons, as nice as this approach looks like, there are often reasons not to take this road, although people have done it and with success. So especially in machine learning community, people are talking about automatic relevance detection, ARD algorithms, and this has many other names. In inverse problems, people are not usually referring to ARD techniques, but I know that in MEG, I have seen people using this, so therefore I chose this acronym here. So the idea is here that you first marginalize away your parameter of interest, Q. And so remember, if you are using these let's say, Gaussian-based methods, you are really integrating here a Gaussian distribution, and so there are even analytic formulas for do that. So what happens is that you are left with the distribution of your theta given B. So this is the evidence. This is called the evidence. And so now you can find the maximum evidence estimate. So you say, what is the most probable value of theta given this evidence? And so you maximize your distribution of theta given B. And then you go back to your original problem. You say, let's assume that this is the value that I trust. So then what is my maximum posterior estimate for Q? And so Q star then would be the argument that maximizes the joint probability distribution given B, where theta is replaced by the maximum evidence estimate of theta. So there are challenges here too, and one is that if you think of integrating a Gaussian, which is not standard normal Gaussian, you know that you have to calculate determinants, and so there's a little bit of work to do when you maximize that distribution with respect to theta. However, there are ways to do that effectively because the Jacobians may not be that difficult to calculate. So and so you can use optimization schemes to do that rather effectively. Well, that's one possibility. What I'm going to concentrate here is the joint map estimates. So I'm simply taking the joint probability distribution of Q and theta, and then I'm trying to maximize the posterior density with respect to both parameters, Q and theta, simultaneously. And the nice thing about this approach is that you have the more or less explicit posterior density formula, so there are no integrations involved. And so you can use optimization techniques to do this maximization in a rather effective way. And so this has been a thread of research for us for maybe 15 years. So we have been looking at different effective algorithms and different hierarchical models so that you get efficient and useful algorithms to do this joint map estimate. And so finally, let me mention the fully Bayesian posterior analysis. So of course, this is what we often would like to do. So instead of calculating just one representative from the posterior distribution, you would like to explore the whole posterior distribution. And so that is usually done by using Markov chain Monte Carlo methods, where you are generating a sample that you draw from the posterior distribution using MCMC methods. And then having this sample, you can calculate the marginalized posterior of the parameter of interest, which is simply the mean value of those Qs. And the covariance matrix is calculated by in this case, I'm using the unbiased formula for the covariance posterior, conditional mean posterior matrix. And so that gives you not only the estimate of the Q parameter, which is its conditional mean, but also gives a sense of the uncertainty, how much you can sort of rely on this estimate. And so this is a nice and complete approach, but it is computationally rather demanding, and so I'm not going to that direction here, although I have to say that this is really the, let's say, the truly Bayesian solution. Okay, so let's start looking at the prior information that we are implementing here. So anatomical information should be used if you have it. And so typically when you're looking at the brain, you know that there are some preferential directions for the current dipoles. And typically the current dipoles are sort of aligned with the neuron fascicles, and depending on the brain region that you're looking at, this may be more or less clear. So if you look at the hippocampus, you know how strongly aligned the neurons are in the hippocampus. If you look at the cerebellum, for instance, there is less structure there. So depending on what brain region you're looking at, you can think that, and if you have an MRI image of the person, or if you have a generic anatomical information about the brain, you may have those directions. So you may know what the preferential direction is, and I'm denoting it by U3. So in a given point in the brain, I'm associating to that point preferential direction U3, which is the direction where I think that the current dipole is directed to. And then there are two orthogonal directions, U1 and U2. And so now if I define a symmetric positive definite matrix so that I take delta, which is a small parameter, times this rank 2 matrix built from U1 and U2, which are the orthogonal directions, and then parameter 1 in the preferential direction, then if you think that this is a covariance matrix of a 3 vector, you see that what we are assuming here is that the variance in the U3 direction is 1, while the variance in the orthogonal directions is delta. So that means that if I'm drawing a vector with covariance Cj at a given point, it is going to show a large component in the U3 direction and a small component in any orthogonal direction. And so the Cj is a good candidate for a covariance distribution of a single dipole at a single position, so that it is favoring dipoles having the direction parallel to U3, and possibly a small component in orthogonal directions. And of course, increasing this delta increases also the possibility of having orthogonal components. And so you could tailor this C for each brain region depending on how strong and good information you have about the preferential directions of the dipoles. Okay, so this is only about the direction of the dipole. So then there is the amplitude of the dipole. And so if you look at a single, okay, so what happened? Okay, so if you look at a single dipole, so the single dipole has a direction that is encoded in the C matrix. And then we are giving the possibility of this dipole to have amplitude that has variance theta j. And so now I'm introducing a new random variable, new parameter, sorry, in the prior of a single dipole, where C sort of takes care of the direction, and theta is controlling the amplitude. And explicitly, my probability distribution for Q given this theta. So the C, by the way, I'm assuming that the C is fixed, so I'm not going to play around with this C. So I'm assuming that the anatomical information is not something that I have doubts about, but the amplitude of the dipoles, of course, is something that I have great doubts about, because that's exactly what I'm trying to solve for using the MEG measurement. So therefore, I'm writing the prior for Qj given the amplitude theta j explicitly here as a normal distribution, where this 1 over theta j is encoding the unknown variance of my J dipole. Now, notice that I need to include here, because I'm going to estimate this theta J2. So I need to include also the normalizing constant here, because the normalizing constant depends on theta. And so if you take a determinant of a 3 by 3 matrix, which has been multiplied by a constant, so this constant comes with a factor to the power 3 out of that, the determinant. And I take square root of that, so the theta j is raised to power 3 halves. And so when I'm writing it into the exponent as a logarithm of it, I will have a coefficient 3 halves in front of it. So this was just a trick to move this theta j from the determinant in front of the exponential into the exponential, and I get this 3 halves here. So the 3, which is easy to forget, comes from the fact that theta is multiplying a 3 by 3 matrix, and so determinant is not linear. It is cubically linear here. So that's it. And so then I'm denoting here again. I'm denoting this inner products defined by Cj inverse by this same notation. So the norm of Qj Cj squared is simply this product Qj transpose C inverse Qj. If I'm assuming that my dipoles are not correlated, which may be a good idea, but may not be a good idea, but this time I'm assuming that. So then if they are independent, then I simply should take the product of all these priors to put together the joint prior, and the joint prior given theta 1, etc., theta n is then a product of these exponentials. So that's my model, which is now assuming that I have an anatomical information of the dipoles. I don't know the variance of the amplitude of the dipole. My dipoles are mutually independent. Okay, so so now we should think about the hyperprior. So what is that we should believe of, or what we believe about this theta j? So theta j, remember, is the amplitude, the variance of the amplitude of the dipole. And so typically in at least many MEG applications, you would like to see something which is compressible. So you would like to find few locations where the dipoles are significantly active, and then you have some threshold under which you don't really care about the activity. And so that means that you are looking for a sparse or compressible vector. So most of the components should be close to 0. And then there is this question of exchangeability, which I'm going to return to, which in this case is now a little bit optional. So often when you are designing priors, you may or may not require that you have exchangeability, so that you are not favoring any particular dipoles over the others. Okay, so that means that the distribution is invariant under permutations of the indices. That's exactly what exchangeability means in probability theory. And so what I'm going to do here is I'm choosing the hyperprior so that it's a fat-tailed distribution. And why is that? Because I want that most of my thetas are close to 0, but some outliers may be there. So if you think of fat-tailed priors, they are fat-tailed distributions in probability theory. They are typically the distributions that are producing small values, and every now and then you have a spike, an outlier. So I'm going to use here a gamma distribution, which is a typical fat-tailed prior. And gamma distribution is having two parameters. It has the shape parameter beta, and then it has the scale parameter theta j prime. So there's a probabilistic interpretation for gamma prior. You probably know that. So gamma prior is sort of the waiting time for, you know, nth event to happen, and so where beta is related to the number of the event, and so therefore larger beta is shifting the mode of the gamma distribution further away from 0. So beta is controlling the shape of the gamma distribution, and theta star is just the scaling. And I'm returning to the scaling parameter soon again. So suppose you have this beta and theta j star, then the independency of the thetas, which I'm assuming here, will produce a hyperprior which depends on two parameters. So my hyperparameter theta by theta is the product of this gamma distribution, which are given here. Notice, by the way, that if my theta j's are different, my probability distribution is not exchangeable because it's not invariant in permutations. But if theta j's are the same, then this is an exchangeable distribution. So my joint probability density is then going to be the prior for q given theta, and then times the product of the gamma distribution. If I put all together, I end up with this exponential expression. So there is the fidelity. Sorry, there is this penalty term for, if you like, of the energy of each dipole with unknown variance theta j. And then there's this logarithmic term. So part of this logarithm came from the gamma distribution, beta minus 1/2. And then I had these 3/2, which came from the normalizing constant of my conditional prior. And then from gamma distribution, I also get theta j over theta j star here. And I'm, for simplicity, denoting by eta this parameter beta minus 5/2, assuming that this eta is a positive parameter. So I choose my shape parameter in such a way that this eta is positive. And so then my posterior density, which is the likelihood times this prior. So here's the likelihood contribution. And then I take the prior contribution, which are these three terms, and I'm adding them together. And so then I have the prior contribution. Oh, by the way, I'm saying this, and I'm pointing with my mouse. I'm not sure if you see my mouse moving on the screen. Maybe not. So I maybe should try to indicate in words, but I'm.
We should, but I'm not seeing it right now. Oh yeah, we do.
You see it. Okay,
Yeah.
excellent. Thank you. So great. So I didn't make a fool of myself. Thank you. All right, good.
Yes. We thought we could have a break at some point in between the 2 hours. So whenever you think it's a good point.
Yeah. Okay. So I'll come to a point, and then I.
Yeah.
Thanks.
Thanks.
Thanks for reminding me. Good. So this is the posterior distribution. So now I'm taking the logarithm, negative logarithm of this posterior distribution, and you get this call it Gibbs energy. So there is this part that depends on Q, and I'm occasionally writing this in matrix notation using this Q capital. So I have LQ, which is in the fidelity term, and then I have this again this d theta norm here, where d theta is the block diagonal matrix where I have these thetas and c's on the diagonal. And then we have the term that depends only on eta at the end. And so this is the quantity that I'm trying to minimize. So my joint maximum posterior density is what is minimizing this quantity here. Okay, so I'm writing it again here. So here is my objective function, and I split it in 2 pieces. So there's a part that depends on Q. And there's the part that depends on theta, and they are overlapping in this middle term, which is encoding our belief about the energy of the dipoles. And so now a very natural algorithm that we called for iterative alternating sequential algorithm, without thinking that the name would stick, but then we started to use that, and so let's call it Ias algorithm. So it is a very simple, straightforward algorithm. So you initialize your theta, you start with these theta stars, which you at this point think that are known, and you set your counter to 0. And then you start iterating alternatingly. So you update the Q by minimizing this EQ theta. So you are looking at the part which is not independent of Q, and you're minimizing that with respect to Q. And then once you have that, you are updating your theta by minimizing the second part, which is the part that leaves out the first term, which is not depending on theta. And then you go back and forth. Okay, so this was an early idea, and so it is very natural idea to go. And so why is this so nice? It is because look at those two terms, the q term and the theta term. So if you look at the q term, which I have written here in part 1, you see it's a quadratic functional. So if you know theta, we are looking at the Iterative regularization problem. So this is a quadratic least squares problem, really. And so this is you're one solve command away from the minimizer of that quantity. So it's a linear least squares problem. What about the second term? So if you look at the second term, you realize that in my second term, the theta j's are uncorrelated. So you can minimize the second term component by component. And not only that, but you can write a simple condition for the minimum saying that the derivative with respect to jth component of theta must be 0, which I have written here at the last row. And so when you differentiate this quantity here, so if you look at it, 1 over theta gives you 1 over theta squared, basically. Logarithm gives you 1 over theta, and theta j gives you 1. So you get an equation which is second order equation, and it has an explicit solution. And the only positive solution is what I have given in the last row. So you have an explicit formula for solving for theta. So what we are going through here is solve a least squares problem, solve a second order equation for each component, back and forth. So implementing this algorithm is extremely simple. Now, does it converge? Yes, it does. So we can prove that there is a unique minimizer. So the functional that we are minimizing is globally convex. So there is a unique maximum posterior estimate. And not only that, but also it turns out that if you look at the minimizer, theta hat q hat theta hat. So it turns out this theta hat is a function of q hat, where the function is this function that we used for the is in the last row here. So this fj is this explicit second order solution formula for theta. So this is the formula that gives my thetas at the optimal point. And so we also have some estimates for the convergence rate of this this Ias algorithm, and it is well, I'm not citing exactly what the convergence rates are, but it is at least linear convergence. And when you're looking at thetas, which correspond to the zero parts of sparse signal or a compressible signal, the convergence of those components is quadratic. So the algorithm converges rather quickly. So we not only have an algorithm which is easy to implement, we also have convergence for that. And I'm going a little bit forward. Let me show you this one. So now we go to the question: why is this? Do we really know that the solution is sparse? And if so, why is it so? And typically, what we have found is that when eta is small, so remember eta is beta minus 5/2. So if beta is small, then the solutions are very sort of sparse and focal. And there is a reason for that. So if I take the limit eta goes to 0 for the map estimate q hat, which depends on eta, you can prove that the unique minimizer q converges to the minimizer of an energy functional, which is 1/2 of the fidelity term plus square root of 2, and then you have the joint sparsity L1 penalty for q divided by the square root of theta j star. Now, this is nice because when you look at this, you know that when theta is small, your solution should be essentially the L1 sparse minimum current estimate basically. And so without having any of those troubles that you have with L1 minimization, because it's not strictly convex. This is strictly convex, and we have a fast converging algorithm to calculate these estimates. So we know that we get something which is close to the minimum current estimate here. There are a couple of disturbing things here in this formula. First of all, remember in the minimum current estimate you have this sort of the regularization parameter. And now my regularization parameter is square root of 2, so it's a fixed number. So why is it fixed? And then there's another strange question. There's this weighting with theta j star. So obviously the result depends strongly on this theta star, but in which way does it depend on theta star? And how could we choose this theta star here? And one could ask, is this theta star somehow related to noise? And why am I asking that is that think about the minimum current estimate or Tikhonov regularization in general. Typically, the regularization parameter is chosen through a process, which is often called the Morozov discrepancy principle. So you're trying to find the solution in such a way that the discrepancy of your solution is about the size of the noise in your signal. And so therefore, the regularization parameter typically will be adjusted according to what the noise is. And there's no simple scaling rule typically for the regularization parameter. You really have to go through this Morozov discrepancy principle. Now we get a formula where there's no uncertainty at all. So somehow it looks like this theta j star here, which is a part of the prior, has to do with noise, but it's not clear how that's possible. And so therefore, obviously more analysis is required to understand what this theta star is. And I think this is a good place to have a small break. So let me know how long break we are having, and I will continue from here.
Okay, excellent. Well, we were thinking of a 15 minutes break, but
good.
So yeah, we start again in 15 minutes. Is that okay?
That's okay. Perfect. Thank you.
I would also have a small. Well, let me just check if someone has a question, or do you have time for a small question in this break?
Sure. Yeah.
So, I mean, I was very fascinated by this last result, which I must confess I didn't know. But my question is basically on the very first part of the presentation, and it's more like a philosophical question. So, because when you say that you put a hyper prior, and because you kind of want to infer the value of the parameter in the prior from the data,
right?
Is that kind of, I mean, from a Bayesian point of view, isn't kind of strange this way of seeing it? Or wouldn't it be I don't know, more Bayesian to say that you use a different prior, or is this wrong?
Well, you can think that you have several priors that you're testing, but so for simplicity, you can think that you parameterize those priors. So you can let's take a simple example. You're planning a picnic tomorrow, and you know that there's going to be some sunshine, but you don't know how much sunshine there is, and so your prior is that there is some amount of sunshine, and so your prior is that, if there is enough sunshine, I'm going to do the picnic, but you don't really know if there is enough sunshine. So you write a prior where the theta is sort of parameterizing that there is some sunshine, but of course you don't know how much, and so therefore your prior is uncertain in that sense, that you need to, rather than saying binary prior, tomorrow is raining or not raining, so that's kind of 0-1 prior, and so we can do that too, and then we can try to juggle between those two priors and try to choose the right prior or the better prior or the more useful prior or whatever criterion you have. But so here we are sort of having a continuum of different options, and given that this option is verifying you, then
Yeah. Okay. Yeah. I see what you mean. Yeah. Thanks.
So there's sort of levels that you are sort of implementing here. So.
So, there was this question by Athena, who's working with Samsung.
Okay.
So the question is, thank you very much for the interesting talk. My question is the weighting in weighted MCE? So does the weighting correspond to averaging over the number of Q?
I'm going to talk about that. So I will give more details about that. So maybe that's it's better that I answer by moving on. And so then you.
Okay. Very good.
Yeah. So thanks for the question. I believe that this is the theta star is the weights have been disturbing us for a while.
I can imagine.
Okay. So whenever you think that it's time to continue, I'm happy to.
Yeah, I think we can go on.
Okay. So yeah, so let's move on. So then no, just a moment. So let's look at this this theta. So recall what in probability theory is called exchangeability. So if you have a probability density of n random variables, then we say that the probability density is exchangeable if you get the same probability density regardless of the permutation of the indices. So that's exchangeability. And so there are, of course, the two famous examples of exchangeable probabilities are when you have IID, independent, equally distributed random variables. So then you have exchangeability. The other classic example is when you are choosing without replacement. So because, you know, the probability of densities is k choose n or n choose k, whatever you use for indices. But so these are the classical sort of the exchangeable random or probability densities. And so if you look at the conditional prior that we have, so this hyper prior times the conditional prior, hierarchical prior, then you realize that the prior is exchangeable with respect to the pairs qj, theta j. So I mean by this that the indices are exchangeable if and only if all these theta stars are equal. Easy to check. So if you look at the probability density, you see that you get the same distribution after permutation if and only if these theta j's are all equal. And why is that exchangeability a good thing? So a priori, you wouldn't think that you would have any preference for any particular dipole. So you look at the head and you say, well, whichever dipoles explain my data, that's fine. And so therefore you wouldn't be, you wouldn't have a particular reason to favor any one of those dipoles. And so therefore you would like to have an exchangeable prior, but the thing is that then these theta should be equal. And so why is that not a good idea? So we'll look at the, here is a toy example, which is a scalar example, easy to visualize and so on. So we are in 2 dimensions. We have a square. And so I'm placing here 3 sources, point sources. And I'm measuring this integral here. So it is like some sort of potential, but it has this 1 over r squared rule, like the dipoles do in MEG. So you can think that these are scalar dipoles somehow. You know, doesn't matter what I'm looking at here, but this is a toy problem. And so then you measure the observed potential around this square, not on the top, and then you try to reconstruct the source. And so we are discretizing this with point sources. So I'm placing point sources in those dots here. So I'm going to have, what do I have? 2,500 source locations and 120 observations around. And so then I run the Ias algorithm with all the thetas equal. And so you get this strange distribution along the boundaries. So you don't even see. So the red dots are indicating the true locations, And so you see here the yellow means that my inverse solver tries to explain the data by placing something just right at the boundary, all over, but inside there is nothing. And so this is the result when you use the exchangeable version of the prior. And so this is a phenomenon which is well known for decades to geophysics and biomedical engineering people. And the reason is simply that the algorithm favors sources that are near the receivers, because you manage to explain the data with lower penalty terms that way. So you're minimizing the current or energy or whatever you're minimizing, and turns out that you get the minimal energy explanation by placing all the sources to the boundary. Well, the commonly used remedy is that you calculate the sensitivity of the source components, and then you do a weighting of your penalty term using those sensitivities, right? So everybody tells you that this is the right way to do, and weighted MNE is doing the same. So that's the W in WMNE. So you put this weight there. So well-known remedy, and it works well. However, so here's what the sensitivity means. So you take the noiseless data L times Q, and then you ask what the partial derivative of LQ is respect to the jth component. Well, that of course gives you the norm of the lth column of your matrix L here. Take the norm of that, and that's by definition the sensitivity of that source term. And so here is the plot where I have plotted the 1 over sensitivity, so inverse sensitivity. So you see that the sensitivity is high and the inverse sensitivity is low at the boundaries, and then so this, you can say this is an insensitivity plot. So the most insensitive point is this point inside here, but because you don't measure at the upper end of the square. And so using this sensitivity, what is the weighted scheme usually? You do the following. So you have the fidelity term here, and then you take the penalty term, but now you are penalizing your Qs according to the sensitivity. So you see that if you have high sensitivity, you put a high penalty. And if you have low sensitivity, you put a low penalty. And so that's the way how you sort of compensate for the sensitivity. And so if you do this, then things usually work well. And so now let's compare this formula to the one that our limit theorem says. So let's go back. So try to remember this formula. This is for scalar sources, of course. I will show you the vector source soon. But so let's go back here. So we had weights here, but the weights were 1 over square root of theta j star. And then was this funny square root of 2 here. So if you compare this term and the weighted minimum current estimate, so to speak, you see that your theta j should be something like 2 over mu squared sj squared. So so it looks like your theta j should be inversely proportional to the square root of theta j star should be inversely proportional to the sensitivity. But that means that you are no longer in the framework of exchangeability, because obviously now you are saying that not all dipoles are equal. You are saying that you should favor dipoles which are deep down in the brain. So why would you ever want to do that? So what is the prior belief that makes you do that? And this has been sort of a discussion in the Bayesian community, at least. So I remember I was talking in a meeting on inverse problems, and I was using this penalty, this sensitivity weighting, and a colleague of mine, a geophysicist who I know for a long time, said that I can't believe that you are doing that because you are Bayesian and you shouldn't do that. And so I had to defend myself. I'm doing something which is sort of considered to be ad hoc. So that has disturbed at least me. Why am I doing that? And so actually it is related now to we figured out this is related to the sensitivity in a way that takes into account the signal to noise ratio. So look at the model B equals LQ plus epsilon. So this is again I'm looking at the sort of the scalar case here. So and then I give you the vector version, so where the sources are dipoles instead of point sources. Okay, so if I'm defining the signal to noise ratio as the expectation of the signal divided by the expectation of the noise, norm squared, both. And so remember, this B here is a random variable for two reasons, for two accounts. First of all, there's randomness coming from the noise, and randomness coming from the prior distribution of Q. So you can calculate the probability distribution of B using those two. And so then when you calculate this expectation, you should take the expectation with respect to the joint density of Q and epsilon. So when you do that, you get the signal to noise ratio in terms of the parameters of your prior. Now, suppose I know that my source is supported in a set S. So 1 to n is the index set indexing the sources, and S is a subset of that. Now I define a restricted signal to noise ratio, which is the signal to noise ratio assuming that my support of Q is in that set S. So that means that my Q is allowed to have non-zero entries only in the subset S in this index set. So that's how I use this concept of support here. So this is a restricted signal to noise ratio. And I'm defining something new here. I'm saying that the problem satisfies the signal to noise ratio exchangeability condition if the following is true. So the signal to noise ratio with a subset S and S prime is equal whenever S and S prime has the same cardinality. So that means that if I know that I have 7 active dipoles, then regardless of how I pick those 7 dipoles, the signal to noise ratio should be the same. So you can think that instead of measuring the exchangeability by looking at the posterior, or the probability density function, I'm measuring the signal to noise ratio or the exchangeability using the signal to noise ratio. And this SNR exchangeability says that the problem remains unchanged for any sampling without replacement of a certain fixed amount of dipoles from your source space. So this is my assumption. And so what does this mean from the point of view of practice? So how should I set up the prior so that I have this signal to noise ratio exchangeability? So assume that you believe that the source space is sparse, and you give the probabilities pk for the support of X. So support of X means that how many non-zero entries you have in your source. And I should use Q and not X here. Sorry, this is a typo. So PQ gives me the probability that I have K active sources. So P1 is the probability that I have just one active source, but I don't know where it is in the space. P2 is that I have 2 sources, but I have no idea where they are, etc. So these PKs are something that I assume that I have. And if I have no idea how many sources I have, I can take these PKs to be equal. So I say that any configuration is as good as the other. And so then suppose that before you start setting up your prior, somebody tells you what the experiment is going to be, and there is an estimate of what the signal to noise ratio is going to be. So obviously we are sort of drifting slightly away from the Bayesian, pure blood Bayesian framework, in the sense that we are already discussing the measurement before we are setting the prior. But so this is typically the case. So when we are setting the prior, we usually know why we are doing the measurement, and so what we are looking for. So I don't think that this is not like and that doesn't do philosophical violence to the Bayesian community. And so now here is the theorem that we found out. So suppose that you are given these PKs, and suppose that somebody gives you an estimate of the signal to noise ratio. So somebody tells you, I'm going to measure the patient, and my MEG device has a signal to noise ratio roughly 10, for instance. Okay, so you take that number, and then you say, whatever my prior is, it has to be SNR exchangeable. So it has to satisfy the SNR exchangeability condition. So sampling without replacement should produce the same signal to noise ratio. Then you can show that the only way that you can choose your hyperparameter theta j's is the theta j star is C over the norm of the Lth column of your forward matrix, where the C has a formula which is relating the estimated signal to noise ratio and the probabilities of the sparsities of the signal. And there is this beta, this shape parameter also. So you get this number C, which you can calculate or estimate at least. And so that's theta. And so that means that in the weighted minimum norm estimate, my theta j's would be, if I use the weight mu and the sensitivities, we see that this theta j is 2 over mu squared divided by the sensitivity squared, where this mu takes now the value square root of 2 over c. So here you see that in some sense, my theta j's, they do depend on the noise, because they depend on the signal to noise ratio, because C depends on signal to noise ratio. They also depend on the sensitivity. And if I use this scaling law and I calculate the solution using the Ias algorithm, this is what I get. So you see it's of course not perfect, because it is highly ill-posed problem, and there is noise and all. But you see that instead of placing the solutions right at the boundary, it pretty much is able to understand that the sources have to be somewhere inside. And so that you have the sensitivity weighting maybe is not such a new thing for people working in geophysics and biomedical imaging. But from the Bayesian point of view, I think this is kind of nice that you have a Bayesian explanation what this weight is doing for you. And so the vector version that I promised, so if you have this anatomical prior, so then your theta j should be given by this formula, where you have C divided by the Frobenius norm of the Lth 3-column block of your lead field matrix, multiplying the square root of the anatomical prior matrix. Of course, then you may have other information on top of the signal to noise exchangeability condition, which makes you want to restrict the theta j's, because you know that what we are looking at is the dipole activity in the head, for instance. And so we know that the dipoles cannot have an energy arbitrarily large. So you may have a physiological upper bound. And so therefore, instead of using this pure scaling law, you may want to clip your theta j star from above. And so we have been trying this, and it seems to be working pretty well with MEG data. And let me see. So then I want to say something about the computational issues here. So remember, the updating step for Q was least squares problem. So we are minimizing a quadratic functional here. So I have written here the quadratic functional using these single dipole models, and alternatively, I can collect things into a single matrix. So my L matrix was the matrix that collected those lead field blocks into one matrix. Sigma was the covariance matrix of the noise. And then I defined d theta to be a block diagonal matrix, where I have these 3 by 3 blocks in the diagonal. And so when I use those, I can simply write this quadratic formula as a quadratic formula for the Q vector. and this should be minimized. So now if you look at this formula here, you see that this is actually a Tikhonov regularized least squares problem, and I'm doing a whitening, so I'm transforming this minimization problem into a standard form by defining a new random variable or new vector. Let's say this is not a random variable, strictly speaking, it's a realization of it. So W is d theta to power minus 1/2 of q. And if I define this W in this manner, and I replace Q by W, so then I find that my minimization problem is simply a matrix where I have both the prior covariance and the forward model in the upper block, and the lower block is just identity, and this quantity needs to be minimized. And so now if you remember what white noise prior is doing and how it is related to the Tikhonov regularization, we realize that this problem that I'm solving here is nothing else but a Tikhonov regularization of an ill-post underdetermined problem, where if I denote by A this matrix, which is the upper block in my big matrix here, so sigma to minus 1/2 L times d theta to 1/2, so let's call that A. So then the upper block here in my equation is A of W equals Y, where Y is sigma to minus 1/2 B. So if you have a problem A times W equals Y, this is typically an underdetermined problem, so we have less magnetometers than we have dipole locations in the source space. So this is certainly an ill-post problem. And so if you need to solve that, well, you can find the least square solution, but that probably is going to be total garbage. So what you do is you regularize, and if you regularize it with Tikhonov regularization, what you do is you add a white noise penalty, and organizing the white noise penalty in one single matrix equation, you get this minimization problem that we started with. Okay, so I'm sort of dismantling the regularization here. And why am I doing this? Because there are alternative ways of regularizing. So what I'm doing here now is I'm interpreting my minimization problem as a regularized problem for an ill-post problem, and then I'm using an alternative regularization scheme. And the alternative regularization scheme is to use iterative solvers, and in particular the Krylov subspace methods. And the method that I want to use is CGLS, conjugate gradient for least squares. So how does that work? So conjugate gradient for least squares is looking for a sequence of solutions that are minimizing the residual y minus AW, restricting your W in a subspace of dimension k. And the dimension k is coming from the spanning vector. So this WK, this vector space k is the span of A transpose U, A transpose A times N transpose U, etc. A transpose A, k minus 1 times A transpose U. So these are vectors, these are k vectors in the source space. And so now I'm writing my solution as a linear combination of those, those source space vectors, and I'm increasing the dimensionality of my subspace where I'm looking for the solution one dimension at a time. And of course, when you do this using conjugate gradient for least squares, there's a very efficient formula and an algorithm to do that. Basically, when you're adding one dimension, you only have to do 2 matrix vector products. So instead of solving a Tikhonov regularization problem where you may end up calculating matrix factorizations, what we are doing here, we are simply iteratively calculating matrix vector products, and we are following the residuals. Now, the iterative regularization means that you continue this iteration until your residual is below the noise level. And immediately when you arrive below the noise level, you stop, because there is no need trying to explain the data better than what the noise level tells you. So we are defining something which is called a quasi-maximum posterior Q-map estimate, where the iteration is repeat it until your residual is below square root of m. And so what is the square root of m? Well, remember that I whitened my noise. So my noise originally had covariance sigma. So I took that sigma away because I multiplied by minus square root of sigma, both the left and right hand side. So now my white noise, my noise is unscaled white noise. And so if you calculate the trace of the covariance matrix, which is the noise level, so that's m, because my dimension of data is m, and so standard deviation is square root of m. So I'm using that whitened noise level as a criterion. And so I'm iterating until my residual drops below that limit. And as I said, what is nice about this algorithm, that only iteration, when you're adding k, you only have to calculate one matrix vector product with A and one matrix vector product with A transpose. So that's a pretty light numerical procedure. And even more is true. So if theta j's are small, as this iteration converges, as I mentioned, this iteration, this IAS converges to essentially sparse or compressible solutions. So the algorithm takes into account the sparsification of the solution. Namely, if your thetas are small, this data d theta has extremely small diagonal components. The blocks, remember, were multiplied by the components of theta j. And so my matrix is essentially a deflated matrix. So the directions where I have theta j already small, they don't count much in this calculation. And so the CGL's algorithm is actually a very smart algorithm. So it takes into account that some directions in the search space where you're looking for the solution, they don't count much. And what happens is that the number typically of matrix vector products needed to solve this updating problem for Q, it very quickly converges to 2 times the support of the solution. So if you have, let's say, here is an example. Suppose you are generating data with 5 dipoles, and then you run this IAS algorithm. After a couple of rounds, your update of the Q is typically requiring only 5 rounds of CGLS iteration, which means 10 matrix vector products. So it really quickly understands what the dimensionality of the problem is. And it's really amazing to follow the number of iterations needed in this algorithm and realize that after a few iterations, it usually understands what the dimensionality of the problem is. So that has been a big source of mathematical interest for us to understand better and to analyze the behavior of the solver. So this is not really the unique minimizer of the problem which we know that exists, and therefore we call it a quasi-maximum a posterior estimate, because this is an approximation. But it seems to be very close to the true map estimate, and so therefore this is one way of going. So here are some computed examples. So here you see the effect of this eta. As I indicated, when eta goes to 0, the solution goes to the minimum norm estimate. And so I took 2 rather small values of eta. So eta is 0.005 in this upper row. This yellow circle here is indicating where we placed the true. So this is simulated data, of course, where we placed the source. And in the lower row, eta is slightly larger, and you see that in the larger eta case, the distribution of the source that we find is more spread out. And so indeed, this eta seems to be controlling neatly the focality of the solution. And so the 0.005 is a good value if you know that your source is focal. If it's less clear for you that the source should be focal, it is rather safe to increase this eta a little bit. So So here is the effect. So here is another pair of reconstructions where we use the anatomical prior, so the C matrix. Remember, I'm using the C matrix to indicate what is the preferential direction of the dipole. And so here I had a two-dimensional cortical model, and so I assume that the dipoles are preferably perpendicular to the cortex surface. And so that was used as a anatomical prior in this case. And so then in the lower row, we took away this anatomical prior, saying that, well, any direction for the dipole is as good. So delta was set to equal to 1 in the anatomical prior. And the effect is, again, that you get a little bit of more uncertainty in your solution, so that the solution is spreading out. So there are sources which have, let's say, a large component perpendicular to the cortical surface, which are compensating for each other, and we have contributions to those dipoles. So the source domain is a little bit spread out, while when you fix the preferential direction, you get more focal solutions. So let me see, how much time do I have? So okay, so I was mentioning in this my title that we are also looking at model selection. So this part of the talk is related to trying to assess how well your solver is doing in some statistical sense. And also what you can test here is you can test different solvers. So you can rank the solvers to some extent with this approach. So typically what you would like to do, so suppose you place a dipole in the brain in the computational framework. So you are simulating data with a single dipole. And then of course you can ask, where does my solver find that dipole? And well, sometimes it's close, sometimes it's far away. And the evidence is kind of anecdotal. So we were trying to do something which is slightly less anecdotal, so that we are systematically asking how well the solver is performing. And so first we have to set up a protocol of generating activity. So we decided to use something which is called the patch activity. So the idea is that you choose randomly, or you choose as you wish, seed vertex from your source space, and then you use a local correlation model, basically the graph Laplacian, and you are generating correlated sources near the seed in a small patch. So you decide how large your patch is, and then you are generating correlated sources nearby that seed dipole. And so that gives you these patch activities. So here you see 3 patch activities. So the colored region here is the active patch on the cortex, and so we have one here in the visual cortex, one in the cerebellum, and one in the brainstem. So those are 3 patches. And so what we do then is the following. So you have an inverse solver. So whether it's IAS or MNE or whatever you want to use, you consider the following protocol. So first of all, you start with the patch activity. So you place your patch activity somewhere in the brain, and then you generate, using a forward model and simulated realistic brain noise, you generate a realistic measurement B. So that's noisy measurement. Then you use your inverse solver and you estimate your Q back. So here is your estimated Q. And so now I define the activity vector by calculating the amplitudes of my dipoles. So now at each point in my source space, I have a scalar amplitude, which is a non-negative number telling you where the activity is in the brain. Okay, so that's the vector, the activity vector. So this is my protocol. So I'm doing this with a patch activity. So then what? I'm asking, suppose I'm taking a vertex Rj from my source space, and I'm fixing a radius, let's say 1/2 centimeter or 1 centimeter. And I'm denoting by Bj a ball centered at that vertex. So then I'm calculating something which can be interpreted as the probability of having activity inside that ball by taking all the activities inside that ball and summing them up and then dividing by the norm of the vector A. So this is some sort of normalized activity. And so we are defining this PA to indicate, so this is sort of a soft indicator if there is activity found in the ball Bj. It's not 0, 1, but it is, if there's lots of activity, this number is large, and if there's little activity, this is low. And so then we look at two different hypotheses. So I'm denoting by Bj0 the ball that is placed around the seed dipole where I created my patch activity. Okay, so that's where the activity in reality is, right? So that's where I generated the activity. So now I'm looking at two hypotheses. My hypothesis H0 is that the activity is detected inside that ball. And I have a competing hypothesis that the activity is detected in some other ball, which I can freely choose from my source space. And then I'm defining a Bayes factor, which is the ratio of these two probabilities. So the Bayes factor, which is comparing the success of my hypothesis H0 compared to the success of my hypothesis Hj. I'm taking the ratio of those two probabilities. And so if you have a good solver and a reliable solver, so then the activity should be found consistently in the ball, which is around the seed dipole, rather than in any other ball. And so if you take any other ball, you should have consistently the probability of finding activity in your seed ball higher than in other balls. And also what you would like to have is that this Bayes factor is large. So there are these famous criteria of Jeffrey, who worked on these Bayes factors, and in his criteria, if your Bayes factor is between 0 and 1, there is evidence against the hypothesis H0. So it looks like the activity is some elsewhere than in the seed ball. If your Bayes factor is between 1 and 3, then the evidence is in favor that the activity is where it actually is. If your Bayes factor is between 3 and 10, there is strong evidence for the hypothesis H0. And then if it's larger than 10, then you have overwhelming evidence. So this is what Bayesian people often use as ranking when they are looking at hypotheses tested against a null hypothesis, so to speak. So so you want to know if your null hypothesis is favored. So maybe null hypothesis is not a good word here because it maybe makes you think of other, like p-value test, etc. So maybe I shouldn't be using that. But so this is what Bayes factors are often used for. You are testing hypotheses in the Bayesian framework. So now we are using that in this MEG framework. And so what we are doing is that we are testing the consistency, how the Bayes factor behaves, doing repeatedly the calculations, choosing these balls Bj all over the brain. And in particular, since our motivation for solving these inverse problems, as I mentioned in the beginning, was to look at the meditation data that Daniela was talking yesterday about. We wanted sort of to simplify a little bit the situation and identify brain regions in a given brain atlas that are active. And so therefore we are doing this testing now brain region per brain region. So suppose you're interested how well your algorithm is doing to identify activity in amygdala. So what you do is you take the amygdala and you randomly choose a seed dipole in amygdala, and then you generate a patch activity in amygdala. Then you do this Bayes factor test, and you are asking what is the probability of, or what is the Bayes factor of identifying the amygdala as the active brain region rather than, let's say, cerebellum. So what you do, you take these balls from cerebellum, and you take the seed ball from amygdala, and you calculate the Bayes factor. If that Bayes factor is large, your algorithm is doing pretty well, because that tells you that well, seems that you are identifying the right brain region. And so then you do it repeatedly with all brain regions in your atlas several times, because you can choose the ball in other brain regions and also in the amygdala, in this case, in different ways. And of course, the realization of the noise is different, etc. So your algorithm should work consistently correctly. So now you can plot a histogram, and the histogram is like how many times your Bayes factor was more than 10, how many times your Bayes factor was less than 10 but larger than 3, etc. And so if you consistently see high Bayes factors in over all brain regions, then you can say that your solver is performing pretty well. And then you can also compare this with other solvers and see how well your solver is performing. So here are some solutions using IAS. This is the top row. So remember, my patch activity was it was somewhere here where I find the activity. So weighted M&E is doing pretty well. DSPM is spreading a little bit out because of its nature, and S-Loretta, which is basically a smoothness prior, is spreading quite a lot of the source. And so now if you look at the Bayes factors, so in this case you would expect that the IAS could do a pretty good job in this brain region, because the found activity is consistently inside the brain region. So here are some other estimates. So this was, we had the activity on the visual cortex, and again you see the focality of IAS, which is a good feature of it. And here is the activity in the brainstem, and surprisingly, even that deep, we find a pretty focal activity. So these reconstructions, they look rather promising. Now the proof of the pudding is in this this Bayes factor, and so I selected from our paper just two examples. So I'm looking at the histogram, the Bayes factor histogram for IAS, which is on the left, and for the weighted M&E. And so in the upper row we have the left hemisphere brain regions, so it may be hard for you to read, and that's important. What is important is that the green bar is how many times my Bayes factor was over 10. The blue bar is how many times my Bayes factor was between 3 and 10. The black bar is how many times it was between 1 and 3. And there is, let me see, there's no, this was red. So green, blue, red, and the black one is when the evidence is against the correct hypothesis. And so where you see green, you see good performance. And so we see that the IAS algorithm is performing consistently pretty well in the cortical area. And if you go to the deep brain structures, accumbens, amygdala, caudate, cerebellum, hippocampus, pallidium, putamen, and thalamus, you still see rather good performance. So you see green and blue here. However, of course, when you go into the brain structure, so if you look at thalamus, for instance, you see that the red bar here is the highest. It says that there is evidence for the activity being there, but the evidence is not overwhelming. Whereas if you look at let's say cerebellum, we see that the evidence is overwhelming. Some of the weighted M&E histograms are not so striking in this case. So we could argue that where you see green, you are doing well. And so we were happy with this this performance of the algorithm. And I believe that this is maybe, I have some generalizations, but this would be maybe a good place to stop, because opening a new can of worms, so to speak, would take more than what I have. And so I thank you for your attention, and I'm happy to answer questions if you have.
Yeah, thanks to you. Thank you very much, Erkki. Very, very, very interesting talk. Let's see, there's already one question by Athene again. We can unmute her.
Yeah, maybe that's...
Probably, Athena, if you try to unmute yourself, you can probably...
Hi,
speak.
can you hear me?
Yeah, excellent.
Okay, thank you very much for a very interesting talk. I got the answer for my previous question. And regarding the first part of this second talk of you, I have another question. If we apply the inverse gamma hyperprior, how does it go? Or do you have any test already that how it behaves, considering the sensitivity for the deeper parts of the brain, if we want to localize the sources in deep region? If I remember correctly, in Calvetti et al. 2009 paper, the inverse gamma hyperprior favors more for the deeper region of the brain.
Yes, thank you. So we haven't been testing it. You are absolutely right. So the inverse gamma is favoring even sparser solutions. That was actually the topic that I was planning to go to. So I quickly show you something from the slides that I have here. So you can in the 2009 paper with Pursiainen and others, we were looking actually a family which we have been revisiting. So instead of gamma, you can look at the generalized gamma family, where you have this additional parameter r, which when r is 1 gives you gamma and r minus 1 gives you inverse gamma. So the problem is with this inverse gamma hyperprior that your objective function is no longer convex, and there is no guarantee for unique minimizer. And in fact, numerical evidence shows that you're stuck in some local minima. Okay, so when you are applying that, you risk missing some of the dipoles. So it very quickly converges to a very sparse solution. And usually those very sparse solutions are reasonable solutions, but they are not containing all the activity. So it's skipping easily other dipoles that are there. So let me scan quickly to a place where I'm mentioning something about this. So what we have been testing recently is what is called a hybrid model. So the idea is that you go first with a more conservative case where r is, let's say, equal to 1, where you know that there's a unique minimizer. And when you are close to a relatively good solution, then you switch to, let's say, inverse gamma. And then it goes really greedily to really, really sparse. So it cleans up the background very quickly. And if you're close to what was the unique global minimum of the gamma distribution target function, then usually the inverse gamma is doing a pretty good job finding something which is similar to that. So my answer is yes, we have tested not systematic with MEG, but what we see with other, let's say, other problems, we see that there are local minima where you get stuck. And in order to avoid that, what I recommend is that you use this hybrid scheme.
Okay, thanks very much. The very short question, another one. the result you just shown for your recent studies of this medication study, you refer to the IAS implementation, which you got, I guess, some very focal activity in brainstem. Sorry that if I couldn't follow very well, but is that also corresponds to gamma hyperprior?
Yeah, this was all done with gamma. Yes, yes.
Okay. Yes. Okay. Then it seems that gamma. I mean, if the implementation was very focal in that deep region.
Yeah. So we had this eta to be 0.001, I believe. So it was really favoring rather focal. I show you the references that. So you were referring to the first paper on this page.
Yes, exactly. Yeah.
Yes, and so the hybrid solver is the second from the bottom, which is in scientific computing Science Journal Scientific Computing last November, I believe. So.
Okay, I see.
Yeah. So it seems to help.
Yes, I will definitely go through the paper. Thank you very much.
Okay, great. Thanks.
So I've been told Karsten Wolters might have a question. Is that correct?
Yes, that's right.
Yeah, please.
Thank you, Alberto. Erkki, hi.
Hi, Karsten. Good to see you.
Good to see you. So we have many data sets of focal epilepsy, and they always share something in common. Namely, if they do surgery, it is not a tiny, let's say, it's not focal like it was presented now in the simulations, but it is rather, let's say, a 4 square centimeter patch that they take out.
Yes.
So I asked myself, where would be the best positioning to make it less focal, but still use sparse priors, because it is only one spot in the brain. So I would have the possibility to use patches in the forward computations to embed it in the lead fields. And then, let's say, for each source node, it is not just one dipole, but it's a small 4 square centimeter patch around that position. Then I could just use your algorithm. Only the lead fields would be broader patches. And if I combine EEG and MEG, it might be even good, because the MEG is more focusing on the tangential, would be more sensitive to the tangential aspects of that patch, and the EEG more to the radial. Or you also showed the eta, which is, let's say, the normal component sensitivity, or let's say the hyperprior distribution. So what would you do so we have that problem, and what is the most important lever arm? Would you put it into the lead field, or would you work on the hyperpriors like Athena asked us, let's say gamma or inverse gamma?
Yeah.
Or would you really go for this eta?
Yeah, so that's a good question, and I don't have a definite answer to you, but I can give some ideas. So first of all, if you increase your eta, it makes the solution that you are finding less focal. So we see the effect of increasing eta. So if you want to use this algorithm without implementing anything else, so then what I would say that one increases slightly the eta so that it starts to you saw this simulated reconstruction.
The eta, do I understand right? The eta, if you increase it, you allow more sources that are no longer normal.
Yes. Yeah. So increasing eta will make it less focal, and so that would be one possibility. The other possibility, which requires a little bit of thinking, is that if you think that these patch activities, however, have a sparse representation. So suppose you are representing your field as linear combination of patches, and so then you say that you only want few of those patches to be active. So what you could do then is to use some sort of joint sparsity, in the sense that one component in your inverse problem is controlling the activity or the strength of one patch. And so that requires some sort of over parameterization, because you don't want these patches to be, let's say, there must be overlap of those patches somehow. And so thinking in terms of patches, and sparse representation of patches would be one alternative possibility. But so if one wants to use directly this algorithm, I would just increase eta and see what happens. So that would be my best guess without any further implementation. Okay, so so it is sort of a basis question somehow. So what sort of basis you are using to represent your sources? Representing the sources as dipoles and saying that in this basis the solution is sparse leads to focal solution. Representing the sources in terms of patches and saying that in this basis the solution is sparse, you get few patches which are active. So
I mean,
the same.
What the danger I see is if I over-focalize this, it will the source that I find is too deep.
Yes, yeah. No, I understand that. So there's when you're doing you know, serious medical imaging, you always have to think about the risks, and I understand where the risks are. So yes, I completely agree. Having two focal solution when the solution is not that focal may be risky. Yes.
I mean, they call it focal epilepsy, but it's never as focal as we know modeled the mathematical dipole now.
Yeah, that's right. Correct.
Okay, thank you, Erkki.
Thank you, Erkki. We still have one question if we have a few more minutes by Alessandro.
Okay, thank you. Sorry, you talked about the model selection and the model choice. And have you ever tried something about model averaging, or do you have some idea about that?
Model averaging, I'm trying to think what that would be. So no, not under that rubric for sure. But so if you think of we had this I had this slide where I was referring to interpolating between models. So where was it? Okay, so maybe, yeah, here. So the example where I'm interpolating between two models, so this is in some sense averaging between the models, and then I'm having this averaging parameter. But this is not probably what you're meaning when you're talking about model averaging. So what we have been doing is let me go back again. So in my references, there were some of the earlier papers here. So no, two more. Here we go. So the last two papers, you see this the source separation term there. So what we were doing here was that we were representing the source as a sum of two sources having different priors. So the source was like U plus V, and U is focal and V is a distributed source. And so then we were trying to choose them between those. So trying to understand which one is explaining the data with less energy. So this is, again, maybe not exactly what model averaging is, but so this is closest that I can get what we have tried. And so if that's not what you meant, then the answer is no, we haven't tried that.
Okay, thank you very much.
Okay, thank you, Erkki. I don't see any more questions, so I think it's time to thank you very much again for your wonderful lecture. And yeah, so I think for today we stop here.
Yeah, thank you, and thanks for everybody, and I wish we see you in person soon. So
let's hope so. Really,
getting out of
really.
this Zoom space and get to the
we have to do this again.
Yes.
In few years, well, hopefully soon in person. Yeah, thank you very much, Erkki, and thank you very much to everyone who was here today. So non-invasive mathematics stops here, goes in pause here now, and resumes tomorrow at 9. Yeah. Thank you very much, and see you tomorrow for those who will be here. Bye, bye, bye.
Bye. Bye, bye.
Bye.